Hello to another episode of It Depends podcast. This time we are tackling something that is so required these days, and that is databases that are capable of handling extreme scale of events, whether it's a Coldplay concert in Mumbai that crashes, or it's Mike Tyson boxing match in that happened recently that took Netflix down and people were not able to see. So this is a space that requires a hugely distributed database, primarily a distributed SQL database. Interestingly, this space, although it's not new, it's been shrouded in a bit of mystery, and some analysts, including some of my former colleagues, have said, oh, not that many companies need this kind of high efficiency, high throughput database. It's a niche category. And then lo and behold, a few weeks ago, we had AWS reInvent, and they announced Aurora DSQL or distributed SQL, which is their foray into this category of distributed SQL. So now we have a number of companies. We already had Google Cloud with Spanner, we had CockroachDB, but I am super excited because today I get to talk to Yugabyte. Karthik Ranganathan is a founder of Yugabyte. Karthik, welcome to this podcast. I am so glad you joined us today.
Thanks, Sanjeev. Thanks for having me. I'm very excited to be here as well. And everything you mentioned, it's exciting. It's an exciting time in the market for databases. It just feels like a lot of innovation coming through, especially as enterprises digitize themselves. So very, very excited to be talking to you about this. And hi, everybody that's here to join us or viewing.
Thank you so much. So, I saw you a few weeks ago at another event, which was KubeCon in Salt Lake City. I attended your very successful distributed SQL summit. It's become like a rite of passage for me to go to KubeCon, whether in Europe or in the US, North America, and then attend your event. And I am very curious if you can share with the viewers what inspired you to start Yogabyte? What was the initial vision for the company? How closely have you stuck to it?
Yeah, absolutely. So maybe I'll go into a little bit of background about myself and my co-founders, and then come into what helped us start. And happy to talk about the first pitch that we did, like what was
I
the pitch
see.
and how much has changed or not. It'd be interesting to see that, right? So, quick background: my co-founders, myself, most of the founding team in
Hmm.
Yugabyte, we all worked together at Meta, called Facebook back then. This was in the 2007 through 13 era. And again, to take you back down the memory lane,
Hmm.
2007, cloud was not a thing, SSDs were not a thing, microservices were not a thing. So there was a lot of things that were not a thing back then. And, we had worked through a lot of these internally at Facebook. Like we had to go what you could call microservices oriented. We had to go adopt SSDs. We had to go adopt commodity hardware. We had to go and architect our systems in nearby and faraway data centers called zones and regions now, and a whole bunch of other things, including facelifting our whole database strategy to become fully distributed as a database, right? So we cut our teeth there. We were the team that built and open sourced, what is now Apache Cassandra. We were core committers into Apache HBase. We collaborated along with the team that built RocksDB, based on our learnings on some of these other systems that we had built, and as well as we were a part of the architectural rev that led to the building of Facebook's current OLTP database called ZippyDB internally, right? So we saw a lot of change that was necessary. At like right from the front row seat in order to building some of it and seeing some of the surrounding changes, right? And the pitch was, I mean, we left Facebook, Kanan and I, my co-founder Kanan and I, we left Facebook to go to Nutanix. Nutanix builds a distributed storage product. That's the one that we were involved in. They built a private cloud and we were involved in the distributed storage part. So it's not a database, but it's still distributed systems. And that really helped us understand enterprise needs and their use cases, right? And so putting the two together, we kind of realized that there's a lot of these hyperscalers coming up with technology that works for them. Whereas in order for the enterprise to truly uptake it, We need the architectural distillation of a lot of things the hyperscalers build, like, Google and Meta, but we need it in a form factor that the enterprises can truly consume, right? Applying this to the database and the data space, we said what we wanted to build was two things. We wanted to build architecturally whatever we had learned through these four database generations that we evolved at Meta, but we wanted to present it in a way that it's not a new API. So people often say, I hate a new database. I don't want to go use a new database. What they mean is if the database is not falling into their mental construct of an existing database and how it makes it better, it's too much work to go and build intuition. Like when developers or architects choose a database today, they don't think, oh, I'm going to pick Postgres here, or I'm going to pick, Cassandra or Mongo, and let me really think about every feature these databases have. They don't think that way. They have an intuitive feel for these are the type of applications that go into a database like Postgres or Mongo or Cassandra or Oracle. They just know it, right? Like that's the intuition that you form. The word evokes that intuition, right? And that's very hard to capture. It's very hard to build. It takes a long time to build. And we said we're going to stick to databases enterprises consume. So we made a multi-API database. We picked, initially, we were thinking of doing MySQL,
Hmm.
Mongo, S3, the object store,
Oh my God.
and Redis. Those were the four.
Wow.
But we knew we wanted SQL and NoSQL in there.
Yep.
So, but it was MySQL and Mongo. This was the first like pitch that we did. We said like, these are the things we see happening. Obviously, when we went down the weeds in order to truly understand the market, the customer, the segmentation, how people have, behavior to build, we felt like Mongo and MySQL are very different. And so that would be taking something that's iterating on the language layer with something that's iterating on the infrastructure layer. So there's too much of an impedance mismatch to practically build as a startup. So we said we'll change Mongo to Apache Cassandra, which was still more like a table and columns and very similar to relational, but still gave non-relational properties, right? And when we also looked at the MySQL side of it, I mean, the market dynamics were such that, Oracle had bought MySQL through Sun, the whole acquisition, and Postgres was looking like it would be the option that would start getting adopted a lot. So we bet on those two. We bet on Postgres and we bet on Cassandra and built those two into the database. So that was the tweak that we had made. But to this day, the vision remains the same. It's a cloud, it's an architecture built for transactional applications for the cloud to make cloud applications simple and go ahead and do it in a way that the enterprises can consume it.
And what are some of the core values that guide your decisions?
So for us, it has to be, so we have a thesis. We have a thesis that, over time, like, and this was a thesis not just out of thin air. This was a thesis of having looked at what happened in a place like Meta, which was born in the cloud, hyperscale tech company. And when we started, what were the pieces of infrastructure that we had? And as time evolved, what were the pieces of infrastructure that stood the test of time? So typically things like disks, right? Like actually locally attached disks started getting used only for scratch space stuff, and everything else was replicated and made resilient. And you'd have stuff like object stores for cheap and deep storage, warm, cold, whatever the tiering in there. You'd have SSDs for transactional. You'd have a warehouse, but all of them were replicated and highly available, and mostly driven by APIs with good observability. All of that stuff, right? So I think that is one area, the cloud native. Let's call this the cloud native dimension. So that drives a lot of the principles of how we build and what we build and so on. The second dimension is, what I was talking about. How do enterprises consume? How does somebody, not just enterprises, like any high value application that's getting built, any business critical application, what does it need? Right. And there's so many databases today, there's really no need to reinvent a new database language. You can
Correct.
always take one and improve it. But the issue is not so much in the language. The language often masks the inefficiencies or deficiencies of the underlying architecture, right? That's really the problem, right? With Postgres, for example, you don't get replicated and highly available, so you have to do stuff. And some of the things it does, if you use it, it's going to make it very difficult to go highly available and replicated with good performance. Similarly, with NoSQL, you get highly available and replicated, but you don't get features needed like indexes or transactions, right? So you have to blend the two worlds. So that's really what, pushes us forward. How true can we stay to the feature set that makes applications successful, and how deeply architectural and cloud native can we make the architecture.
So, Karthik, amazing trip down the memory lane and the core principles. I am dying to go deeper into the technology, the building blocks. But before we go there, I have one last question, and then we'll pivot to technology and geek it out. The last question I have in the section is, can you please share how people are using Yugabyte, some real life use cases, customer success stories?
Yeah, absolutely, absolutely. So, and it's always great to talk about, like, I think this is one of your philosophies also, Sanjay, which resonates with me too. It's like better to talk about the use cases, so the rest of it can be like, okay, with this in mind, let's think about the rest, right? So, we have some great use cases. Like, I think really, really proud of what we've been able to achieve. We have some of the largest enterprises in the world running some of their most mission critical workloads on Yugabyte DB, right? So, I'll talk about ones that, the viewers and audience may be able to connect with as use cases that touches them in daily life, right? So one of our use cases is like one of our customers is Paramount Plus, and they do a streaming application. So they run a lot of shows, very interesting shows. So shows from, like, for example, the AFC's American football, like various games, like the Super Bowl, like this year's Super Bowl, for example, used a Yugabyte database in a very critical path, like Champions League, Grammys, Oscars, like a lot of
Oh,
these events, right?
yeah.
And when you think about each of these events, the hour leading to the event usually sees a huge spike in the number of people trying to log in and watch the event, right? And that means some infrastructure needs to authenticate these users, needs to pull up their profile, needs to get their preferences, needs to attach them to the stream. So
Mhm.
that needs to happen. The identity and authentication needs to happen. Or sometimes they may want to pay because they are new users coming in. It's a revenue stream. They may want to renew, they may have forgotten to renew, or they may already be renewed and they can just go in and get the access. So they may want to do a one-off subscription for this season alone. So there's various things that happen even from a revenue perspective for the company. So a lot of this is handled by Yugabyte DB, this part. We don't obviously stream the show, but it's the thing that lets you get access to the stream, right? And
Mm.
so when you think about it, millions of users log in the moments leading to the game. And if you take the Super Bowl 2024, for example, it is actually in history one of the largest events. It's actually the largest online event, I believe,
Oh,
ever.
wow.
123 million users total, more than that actually. And when you look at how it functioned from a database perspective, the hour before everyone's logging in, halftime show, a new crowd is logging in because Super
Mm.
Bowl ads are really amazing. Taylor Swift show, yet another crowd. The last few moments of the game when it gets nail biting or people want to see the finish, post game show, different people logging in and out throughout, right? So we have to handle that kind of a scale. So that's an example. Another daily life example is like, the General Motors smart vehicles, right?
Mm.
Try to do an emergency roadside assistance call, when you try to, unlock your car from the cell phone, or you turn on climate, a lot of this stuff gets powered by Yugabyte DB. That's the database they eventually write to. So that's another one. And, we're seeing a lot more than that, actually. We have, I mean, this is something I can't yet fully go public with, but we have a large nation actually using us in their critical stack for mobile payments. So, all of the digital payments are, now going through Yugabyte because high scale, highly resilient, always available. Because, when you think about mobile payments, when people render service, you pay them through the mobile transaction. So it just has to always work. So
How
yeah, these are
many,
some of the
yeah.
examples.
How many transactions are we talking about? I know this is, you cannot mention the name, but what's the scale of these
It's
digital payments?
billions of transactions. So you could think of the
A
largest
day?
countries in the world. Like it depends on the type of transactions. Yes, in the order of days a day, and these are payments that are not exactly like it's not clubbed together. Individual payments, like I know a
Yeah.
few dollars here, a few dollars there. Each of those micro payments goes through the Yugabyte stack. It's in terms of population, is one of the countries that's up there. So when the time is right, I will share more. We can do
Okay.
another one of these,
Perfect. Yeah.
but it is a pretty sizable, you know,
Yeah.
um, national piece of infrastructure for them. So it is pretty huge for us, and it just goes about to underscore what are some of the underpinnings from a data perspective of an
Right.
increasingly digital economy.
So to build a database of this scale, what would be at the highest level? What would be the building blocks of a distributed database?
Yeah, this was the fun part. This was the earlier stage of our company journey. So I'll just
Hmm.
outline a few things. I mean, there's a number of things one has to, think about. Like, like I said, we're a team that has built three or four databases. A bunch of us have done that. We've seen databases on the relational side, non-relational side. So we bring all of that experience.
Hmm.
But I'll just try to boil it into some high level things that we thought about, like very, very high level, right? So the broad things we had to think about are number one, how are we going to do the storage engine? Like,
I
what is the
see.
storage medium itself? Number two, how are we going to do the replication, distribution, sharding, all of that stuff? So it's the replication piece
Hmm.
of the stack, replication and sharding. I'd say, well, maybe those two together. And the number three is when you think about, we were building a transactional database, a relational database. So transactions are the building block, and multi-row
Hmm.
transactions are super critical. And when you have distributed data across different nodes, you have to think about synchronizing time. So number three,
Hmm.
how we synchronize time, because time can have variance across nodes. And that's okay for practical purposes. When we look at our computers and we look at the time and it says it's 11:25 versus 11:26, it's okay. But from a actual payments or like some of these use cases we talk about, like, are you able to access the funds in your bank, or did
Yeah,
that actual credit debit happen the right way? These things become super critical. So that's another one of those areas. And then lastly, I would say the last and most critical piece is to take all of these building blocks and map it to something that users can consume right away, right? So it's very difficult for users to come in and learn all of this stuff and learn how to use to build applications and then build or move their applications. That's too much work. It has to be packaged in a way that they can quickly access this stuff while having all of the technology underneath to empower them to run in a cloud native architecture. So I'd say those are the four top
I see.
things: storage engine, replication and distribution of data, time synchronization, and how we present the APIs on top.
Excellent. In fact, I got reminded of Dr. Werner Vogel's keynote at the just concluded AWS reInvent 2024. He spent an inordinate amount of time talking about time sync and the concept, and it was fascinating to see him go into that. So we are now, with your permission, let's go into each one of these building blocks.
Let's do
So
it. Yeah, let's do it.
okay, let's start with storage. So when you say storage is a critical starting point, what do we mean by that?
Yeah, so there's a few different things. I mean, storage at the lowest level, when people
Hmm.
think of storage, they think of a disk, right? Like, or like whatever kind of disk. You can store
Right.
stuff on disk. But that's not all that I mean when I say storage. There is, what happens if the disk fails? Well, then you need to now introduce replication and rebuild and repair, right? And then what happens when data doesn't fit on a single disk? Well, now you have to introduce sharding and distribution. So there's a bunch of different things that you start introducing, and all of that together comprises the storage engine for Yugabyte DB, right?
Hmm.
So I'm putting all of that together. Now, some of the broadest strokes there, the first point to consider is the way you lay out data on disk, right? If back in school, when I was in school, it's been a while, but when I was in school, I don't know what they're teaching nowadays, but when I was in school, B tree used to be a big thing that we had to learn because
Yeah,
it was the
that's
most
right.
efficient way to lay out data on disks.
Hmm.
Disks meaning hard disks back then. There were no other kind. And you had to minimize the IOPS in a hard disk in order to extract the most from it, because disk is rotational. It has to do seeks. Every time you seek, it's going to be, kill your latency, and it's going to have a disk can only do so many IOPS per second, so many seeks per second. If you ask it for too much, it won't work, right? So that's the way most of the traditional databases got built. But like I said, at Meta, when we switched over from hard disks to SSDs, we found a very curious problem. The problem was the amount of actual throughput you could get from the SSDs was not as high as it could be. We could never drive the SSDs to its maximum utilization one way or the other, because the way we were storing data was minimizing IOPS. And
Hmm.
SSDs actually do really well if you put a lot of IOPS on them.
Hmm.
So you have one piece of hardware technology which says don't do too many IOPS, you'll be fine. And you have another piece of hardware technology which says do a lot of IOPS in parallel, you'll be able to utilize me better. right? So that kind of brings the first issue, right? Impedance mismatch. And the second thing is the memory on these machines started getting big. So when you go to cloud native machines, you get cheap machines that can fail anytime, but you get a decent amount of memory compared to traditional machines where the memory, ratio was lower. So now you can do better caching, you can do better things in memory. And what you want to do is for once you've crossed a certain threshold in the memory, you can actually do a lot more in terms of storage if you lay it out right. So that means the memory to disk ratio, you want to support a lot of disk for every bit of memory, right? And below a certain threshold, that's hard to do, but above a certain threshold, that is actually possible. So these were the two fundamental things that drove us to think about how do you actually do storage, right? And we said we are switching from B tree to log structured LSM trees, right? So it's a different way of storing data, very friendly for SSDs. You can drive insane number of IOPS as well as it's friendly towards the way SSDs work. And that also lets you, support a deep storage with reasonable amount of, RAM. So that was the first set of things that we had learned at Facebook. And this was when we were building Apache Cassandra and HBase, so 2007 through 2009 or 10. So this was the time when we started, extracting more. We had built initially for hard disks, and then we switched over to SSDs and saw that for SSDs, it does a lot more. So around that time frame is when we started looking at this stuff, right? Um, when in our own journey, Cassandra and even though they were built for hard disk, they still had to be built for cloud machines. So Cassandra and HBase were more LSM based. And then when we went to hard disks, we found that the language of implementation was super critical. Java couldn't keep up with the speed of
Hmm.
SSDs. Garbage collection was an issue. So we moved over to C++. And we built RocksDB, which was LSM oriented, and we made a storage engine and put it into MySQL. It's called MyRocks, and that's what Facebook used in order to achieve efficiencies in a cloud native and SSD oriented fashion, right? So those taught us a lot about the storage engine, and that kind of is the underpinning for Yugabyte as well.
I love this conversation because you bring the historical aspects to walk us through why we needed to rethink from the traditional way of hard disk driven storage to the more newer technologies like SSDs. I am also very curious about NVMe's and the is that does that cause more changes? Like if you've got these, hard drives that work at the speed of RAM, but at the cost of SSDs.
That causes some changes, but not a whole lot. And
I
I'll tell
see.
you, it's
Okay.
actually interesting, right? What causes changes and what doesn't, right? Even though it's directionally, it looks like hard disks to SSDs, the jump is similar to the jump from SSDs to NVMe. I think the real problem is that, you know, like again, like let's look at the economics that drive this, right? So
Mhm.
for hard disk, when you're trying to do, whatever kind of database, you
Hmm.
need about we could at Facebook we or at Meta we found out we could support a 1:2 to 1:4 ratio
Hmm.
of RAM to disk. So every gigabyte of RAM, we could do 2 to 4x the storage with a B tree based model. When you switched from a B tree based model to an SSD based model, this goes up to a 1:100 to 1:250. 250. So it's huge difference, right? So I mean, obviously, all of the data cannot be warm. It has to be like the warm data has to, but the addressability of the data and what you can maintain just goes up through the roof. So we were running nodes that had many tens of terabytes with only like a decent amount with a reasonable amount of RAM, not like a crazy amount of RAM. But when you go from this to the NVMe based storage, I think what we find is your disks get much faster, but
Hmm.
your network latencies are still the same.
Hmm.
We already said one of the postulates of cloud native is you need your data replicated and redundant.
Correct.
You cannot keep the data in one place. So it cuts it out for an aspect of storage because
Hmm.
ultimately, what are you getting more of? Are you getting more processing, lower latencies? Are you getting more storage density? Are you getting faster, right? What are you getting that really improves the end-to-end system is the important thing to ask, right? So what it turns out you're getting is ability to access a lot more data quickly, even though it is going to the disk in order to do a seek, right?
Hmm.
But you're always accessing it from a client that's remote, right? So that means you go jump over the network, it's an order of millisecond latency, and then you're cutting whatever is behind it from maybe 1 millisecond to even zero point 0.1 millisecond. So
Hmm.
your end-to-end latency is going to look like, say, 1.6 milliseconds to 1.1 milliseconds, or so it's not a dramatic improvement.
I see. Oh, got it.
That said, when you're analyzing a large amount of data with
Yeah,
some of the data local, it could help those more of those caching kind of use cases. So
I
it could
see.
help in some use cases, but it's not a fundamental shift because other parts of the stack also have to catch up.
Yeah. So that takes us to the number two building block, which is replication and sharding. And you start talking about that when you talk about the network bandwidth. What is the theory behind replication and sharding?
Absolutely. Yeah. So two basic principles, right? The first principle is that you cannot lose data, right?
Yeah.
And you cannot work hard to protect your data. Work hard as in people cannot be working hard to protect data because as your machines become commodity, your incidence of failures goes up by at least two orders of magnitude, which means if you had a probability of a machine failing, P, like whatever that is, you're looking at 100 P right now. Right. So and it's not an outright failure. It's like network partition here, this thing slows down, that thing misbehaves, this is flappy. You put all of this stuff and the number of times it happens per day, you're looking at 100 times P for any
Hmm.
individual component, right? So assuming that if the probability of P hits, somebody is going to go fix that thing. The problem is it's 100 times that. You can't have somebody keep fixing it. You can
Hmm.
never catch it fast enough. So therefore, you need an inversion where the architecture takes care of this and then presents the failure to the person that will take care of it, and they can do it at business hours and do it in bulk rather than have to react to every single one, right? So that's the meta construct of availability and resilience, right? The second thing that we see a lot of is that we cannot have bottlenecks, right? So whether it's bottlenecks and downtime, like that's something that somebody in the cloud abhors because again, back at Meta, what we found is when one country is sleeping, another country is wide awake, right? So there's no downtime and APIs never sleep. When there's an API
Hmm.
based CI/CD integrate, there's no sleeping. So there's no, you could put out the notice between 12 a.m. and 12 midnight and 2 a.m. and get the stuff done. That doesn't exist anymore because there's no 12 to 2 a.m. It's always something going on. And the second problem is how many of these things are you going to do between 12 and 2 a.m.? There's not enough days in the week and days in the year in order to get this done to periodically refresh because things are growing at an exponential rate, right? So this means you need self-regulating systems.
Hmm.
So bottlenecks, failures are the two things we wanted to eliminate because failures are the norm and bottlenecks will kill you because you have to be able to, scale out at the drop of a hat, right? And if you don't do that, if you don't have either of these, it will impact your end customer acquisition and user experience because users are like, look, this app doesn't work. I'm going to go to their competitor that seems to work all the time. Or even worse, the brand damage. If these guys can't deal with this, how are they going to deal with more critical things? And I'm just going to switch my business to somebody else. So it has an implication. And what you don't want to do is pre-provision to 100 times the size because there are too many services and you don't know which one will grow how. Right? So
Correct.
all of these coming together makes it super important. Some of the core things we thought about in this area: how can resilience become transparent to the user? Which means every time there's a failure, suppose we come back and say, you could lose up to 1 minute of data. Now your application architecture gets complicated. You have to deal with
Hmm.
what data you lost. Is it okay? Can you still figure out consistency? We didn't want to have that trade-off, especially where the latencies were manageable within a single region, right, or data center. So that was one of the areas where that became super critical for us. We adopted Raft, like a consensus protocol. And the other thing that was important was no bottlenecks. So read, writes. I mean, you hear of single writer, multi-writer. We wanted to go multi-writer ready from day one, multi-reader ready from day one, right? And don't differentiate between consistent reads and replica reads. Just make it all the same, and you can send your queries to any of the nodes, and they'll take care of it. So a symmetric architecture. So some of these things became super critical from a replication and the distribution of data perspective.
So what we are saying here is that in a distributed architecture, you've got multiple nodes, and each node is has read and write capabilities synchronized to each other. And then in case of sharding, you sort of you basically divide the data into like using a shard key into different options. but using the replication, they're all active,
They're
whether
all
you,
active, active. Yes, they're all active, active.
excellent.
And we give one of the explicit choices we made was the way it would impact applications is ultimately people needed latency to be in control, throughput to be what they wanted.
Hmm,
That's the more important thing, right? And so we trade off like within a region, we always do active, active,
hmm,
active, 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 at least three replicas, and zero data loss auto failover, right? And the
yeah.
failover time is like less than 3 seconds. So it's
Hmm.
usually something that any other component of the stack can fail for that long. So, you don't need to be zero. You just don't need to be bad enough to be noticed. That's the important lesson there from practical systems building perspective. And across regions, when resilience of data, when an entire region goes down becomes important, we give optionality. We give synchronous or asynchronous or a number of different building blocks. In fact, we have about 8 building blocks. Each of them leads to a different combination of SLAs you can achieve from
Hmm.
data loss, auto failover, latency, throughput. So, and depending on what you want, you can dynamically switch between these, right? So it gives you a whole new world of possibilities in the cloud, in the cloud architecture side.
One of the critical things for this active connection is the number three building block, which is time synchronization.
That's right.
How has the time synchronization progressed over the years, just like, the storage and other aspects?
Yeah, I think this is a very exciting topic from I don't know, self contentment and happiness perspective for me personally. So I'll just explain
Yeah.
why. We started Yugabyte in 2016, and we had to pick the architecture fairly early on. So 2016, 17 early, we had to pick the architecture, right? And if you look at what were the strategies to do, like we knew we wanted to build a transactional database, that was pretty clear, and we wanted to go cloud native. So all of that was pretty clear. In designing the architecture, we had a fork down the road, right? If you want to synchronize time across machines, ultimately we all understand why that's critical because if I transferred money to your account, if I transferred $100 to your account at 10 o'clock, right? And you better receive it at 10 o'clock. If you receive it at 9:59 or at 10:01, that's
Hmm.
going to cause a problem because if there's a failure, if something happens, we could end up in a state where I'm missing the $100 and you don't have that $100, or I have the $100 and you have the $100, neither of which is a good,
Yeah.
sustainable outcome. I mean, maybe we're personally happy in one case, but that's fine. It's not sustainable,
Yes.
right?
Yes.
So,
Yeah.
we all understand why that is the case, but there are two ways to do this in a cloud environment, right? You could do it with a central, what is called a timestamp oracle. So you could all go to a central location and get the time from that
Hmm.
location. Central location keeps giving time, and everybody uses that time. There's no 10:01, 9:59 because one person is issuing the time, and
Correct.
they'll give us both the same time, irrespective of which nodes our data sits on, right? The problem with this approach, the first real production use case for this approach was called Google's Percolator project.
Hmm.
And Google's Percolator project, the problem was it had a single bottleneck, a single point of failure, which you
Hmm.
can make highly available by switching it over to a different place. But let me give you an interesting scenario in a distributed environment. We're running transactions across US and Europe, let's say, right? And you have three replicas of a transaction in Europe, and you
Hmm.
have three replicas of transactions that happen in the US. Where would you put your timestamp oracle?
Hmm.
It's got to be in the US or Europe because occasionally I may want to do a transaction that hits both sides, right? And most of the time, I want to do either Europe or US, depending on the user that comes in, the US user or the Europe user. So if you put the timestamp oracle in the US, and let's say it gets partitioned from the Europe side, what happens to the transactions in Europe? They stop,
Hmm.
right? So the problem with this type of an approach is you have to detect it as one more piece of, service. And you have to deal with all the resilience combinations, cross combinations with whatever goes on, right? And that's a really big problem, right? And what we felt the other fork in the road was what Google had done with Google Spanner.
Hmm.
Obviously, they had built all these satellites and a fantastic piece of architecture where they say no two nodes, doesn't matter where they live, are more than 7 milliseconds apart. And they
Hmm.
will just wait for 7 milliseconds and they know both nodes have caught up on time. So there's no, in our case, 9:59 or 10:01. If I exactly transfer it at 10, they will wait for 7 seconds or 11 seconds past 10 o'clock. And they both know we're both caught up. because it's all cross 10 o'clock, and they'll give the time 10 o'clock at 11 milliseconds past 10.
Milliseconds, yeah.
11 milliseconds past 10 o'clock, they'll use the time as 10 o'clock because
Hmm.
we have both crossed 10. That's the guarantee that's, true time gives us or gives them, right? Now, our belief, our bet, ultimately building a business is bet. One of the bets we took was that, the technology would go to a direction where more and more cloud providers would start building better and better time synchronization. Because we'd seen the importance of this inside Meta, and Meta has already built, right, their own, true time equivalent, right, their own
Hmm.
accurate time sync service. It's very important for cloud systems. This is a fundamental building block, right? So it's really exciting for me about, Vernal Vogel's talking about time and the whole time
Yeah.
sync and precision clocks that they're bringing, because this really validates the hypothesis. And now the US user can do their transactions in the US, the Europe user can do it in Europe, and you can occasionally do it across, and we can actually do it better with a better latency because of our unique approach to using a hybrid logical clock than what you would get with even just a hardware clock with like a true time a GPS based clock. So I think that's really fantastic to see all of this happen in the market. This was a thesis we had laid down, and this was we'd bet, more than what people might realize on this being the path the industry would go in. So very validating to see that happen.
What, so there's some concept that just crossed my mind. Lamport clock. Can you explain what
Yes.
that is? And there's this concept of NTP. What does that stand for? And where does that fall in this?
Yeah, so we use what we call a hybrid logical clock.
Okay.
So there are two parts to it. When you look at time, and for example, you can say, hey, the time right now, based on the clock I see, the physical clock I see is 9 o'clock, right? Whatever that is. That is a physical clock,
Hmm.
right? Obviously, there's a time zone that matters. And in the world of computers, we go to UTC time, which is like we
Hmm.
convert it to milliseconds or whatever. So basically there's a forward moving time that's universally accepted that is represented by 64 bits, right? So you have that as a forward moving clock. The CPU keeps bumping that up. If your CPU is slower than another machine CPU, you get the rates at which time moves forward to differ, right?
Hmm.
So I would have moved 1,000 units forward, the next machine could have moved 1,005 units forward, and there's a problem, right? When you install NTP, it will bring all of these times across different machines into synchronization.
Hmm.
So what it's going to do is it's going to say, okay, look, you clock that's running at 1,005, you are running faster by 2 units of time, and the machine that's running at 1,000, you are running slower by 3 units of time.
Hmm.
You guys need to adjust it. So one person like slows down or jumps back, the other person jumps forward. All of this stuff happens. Okay. The problem with an NTP like synchronization, you could see a variance of 100 to 150 milliseconds in practice,
Hmm.
right? So if you're 150 milliseconds apart and you're using a system that's doing, 100,000 operations a second, you're going to get a lot of issues with transactionality. So in those examples, our transfers, well, we both have the money or we both not have the money, and it's not good, right? So that is not viable. So another approach in computer science was to go after, forget this notion of time. Let's use logical time. Let's use counters. And, everybody, and we talked about how a single person can issue this time. But if that's not good, what we can do is machines can talk to each other. And every time they talk to each other, they'll say, hey, I am at 1,001. So, you tell me what you are at every time we talk to each other for whatever purpose. So if you were at 1,003, I'm going to bump up my time to 1,003 and go from there. And if you're at, 900, 999, you're going to go to 1,001 or to whatever I tell you, right?
Hmm.
So that way, every time somebody talks to somebody else for purposes of, causality, A talks to B in order for B to happen after A, right? So you get the time synchronization by bumping up these logical clocks. The problem with the logical clocks is A, they're very difficult to operate in practice because you cannot say, give me a cut as of some timestamp. It's very tough to do that, right? So it's like it doesn't have a relevance in the real world. And secondly, it gets very slow performance-wise. There's a lot of stuff you have to do, and you still don't catch all the edge conditions. So what we do, we married the two sides together. So Hybrid logical clock brings together NTP on one side, coarse
Hmm.
synchronization, with vector clocks on the other side. Within that coarse window, can we do the time tracking? So you're broadly able to move forward with time, and inside that, you're able to go much more fine grained, giving you the best of the two worlds, right? And here's the really, really cool trick that we did at Yugabyte for building Yugabyte DB. I see this often posted in some online forums, and they don't see this nuance. It's a 64-bit number. If you make it a different number of bits, you cannot reuse it as time because it's going to be a different
Hmm.
structure. It's going to cause a lot of problem in terms of
Yeah.
performance. So we wanted to retain 64 bits, but how do we get Lamport clocks as well as the physical time inside the same 64 bits? So we said 52 bits gives us up to a microsecond precision, and the remaining bits gives us a logical counter. So we use 4096 for logical and the rest as physical, and we group operations inside these windows. So we'll give it a timestamp, and if 10 operations happen at the same 64-bit number, we'll give it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 because they're so quick you can just order them. You don't need time synchronization for them. So a lot of things to say. We worked on that performance to really get it out.
Wow, this is turning into literally a lesson on how to build databases. I have one more question, then we move to higher levels. We are doing all of this time saying, obviously, because we want transactional guarantees of consistency. When Aurora distributed SQL, DSQL came out a few weeks ago, they talked about optimistic concurrency control, and I see there's a lot of discussion going on different social media forums as to differences between optimistic and pessimistic. So, can you walk us through how should we think about different isolation levels and how to understand this?
Absolutely. Yeah. It's almost a black art kind of a thing because it's very confusing. People
Yeah.
use overlapped terms all over the place. I think there are three dimensions to think about.
Hmm.
I'll explain the dimensions, and only one of it matters to users. The others are more for builders and more
Hmm.
theoretical researchers and so on, right? The first one is the isolation level as defined by academia. So a particular database will give it a name,
Hmm.
but two different databases may pick two different names, but fundamentally it needs to map to something that academia knows as this is the algorithm and this is how it works, right? So the theoretical way of explaining isolation levels are like, and they increase in their level of strictness and perhaps decrease in their level of performance, right? That's really how it works. But you have things like snapshot isolation, or serializable snapshot, or serializable, or linearizable, or so on and so forth, right? What it really tells you is what is the expectation when there are two transactions running concurrently? What can you expect, right? So one mode is each transaction looks at the state of the database as it were before it performs an operation, right? Reads, writes, everything. And then it keeps doing all its operations. And two transactions can use their own individual copies of data, make their changes. As long as the changes don't conflict, which is the writes don't conflict,
Hmm.
they're able to both write, right? So an example is, let's say I have two different transactions in which I'm trying to transfer $100 to you. Okay. I have, say, $150 in my account. So I can't do it. I should fail, right? Now, if you used something like a snapshot isolation by itself, my first transaction would go read my balance. It would say 150. And before it does anything, the second transaction would also read the balance. It
Hmm.
was 50, right? And now each of them is okay to do
Correct.
$100, right? And when they write it back, it would fail,
Hmm.
right? Because one changed it, the other changed it as well. They both can't change it, it'll fail, right? So this ability to catch the error is called an isolation level. In this particular case, it's called a snapshot isolation because you take a snapshot of the data and operate on it, right? So if you didn't write back or you wrote a different row, this would succeed. It's okay because
Hmm.
it's okay that you. Now, serializable says something differently. It says that if as a part of a transaction, one of the transactions is going to decrement, the other transaction cannot read the prior value, it has to read the post value. So this is the theoretical construct.
Hmm.
Now, let's say there's a conflict. In our case, let's say that you're trying to reduce $100 and it conflicts. What do you do after it conflicts? Do you throw an error back to the application? Or do you, on behalf of the user, do you say, look, I know that this other transaction is trying to reduce $100 from the same thing I'm trying to do something with. So I'm going to wait behind that transaction, let that transaction succeed, and I'll come back behind it. These are two fundamentally different approaches. In one approach, you kind of assume that there's not going to be too many failures. So let me just tell the user if it happens, because it's very rare. It's called optimistic
Hmm.
concurrency control. You're very optimistic. It's not going to happen, right? And the other kind is more like it could happen. So, you know what? Let me just make sure that I mark that this row is going to change. And if somebody else comes, they can wait behind me because somebody is going to come. And this is called pessimistic concurrency control. So, in one case, you build the retries into the application. In the other case, the database
Hmm.
does the retries, right? This is at a different dimension from the isolation level, which can be whatever it is. It can be serializable snapshot, whatever it is, right? So, this is what happens when you detect a conflict. And the third one, which is the only thing that matters, is that Oracle and SQL Server and DB2 and Postgres, they all support read committed, which is a combination of the isolation level guarantees of what you can see in a transaction, plus is it optimistic or pessimistic? It goes together, right? And so Postgres has three practically important ones: read committed, repeatable read, one level higher, and serializable, the highest, right?
Hmm.
And you have to build it into your transaction, distributed transaction and conflict detection and retry. All of that is a layer that you have to build. And it has an architectural underpinnings on even how you issue time and how you use time and all of that stuff, right? So that piece with Yugabyte is exactly what Postgres supports. Most of the databases out there are read committed in isolation. And I often joke, like, we found product market fit through read committed isolation. It's a joke because our customers came back and told us, look, if you're not supporting this, we cannot move those apps because we cannot reason about failure cases. And this was not one, there was a series of 8 or 9 such features, but this was the first one of them. And we said, like, at this point, our customers understand exactly what we need in our roadmap for exactly what it is that they need, right? So that was a very interesting way to look at the market pulling our roadmap rather than us pushing it to the
Oh,
market.
very
So
interesting. So, Karthik, amazing. This is such a valuable lesson of trying to understand this black art of consistency. So, I want to change tracks and I want to go a level higher. We've gone from storage, the raw storage, to replication, to time sync, to consistency. Let's talk about Postgres. So, you are Postgres compatible, but that is also a very loaded term. What are the different ways of Postgres compatibility that you see in the market, and how does Yogabyte differ?
yeah, I think rightfully everybody, when they see something is working, will try to double down on it, but
Hmm.
your architecture decides how far you can go. So when people say Postgres compatibility today, we see a few different variants. We see, like, for example, Google Spanner had its own dialect. Google Spanner was built internally for Google, and
Mhm.
it's a fantastic piece of technology, but it's not Postgres. They didn't need it. They needed whatever they needed, right? So just like at Facebook, we never built stuff for the enterprise. Like I had already told you that, and we learned that at Nutanix. That, oh, wait a minute, this is the gap, right? So
Mhm.
kind of similar with Google, and they had built their own thing, and they felt like it's far easier for users to use this through Postgres. So they said, okay, let's make a thing in front which would make it easy to use the Postgres drivers. And let's support a little bit of the Postgresism so people aren't completely lost on how to use this thing. So we'd call that driver compatibility, right?
Hmm.
And then there's a level above where you say, use the same syntax as Postgres. If you do whatever you write in Postgres is recognized by the database, but it may not do it the same way. It may choose to ignore half of those statements because we don't really understand it. We cannot do it for whatever reason. We're a different database. So that's more of syntax, compatibility. So we see somebody like, for example, CockroachDB falling in the syntax. And the level above is semantic. Semantic is like Postgres has a feature. I'm going to re-implement the feature in a different way, but you need to go figure out the nuances of how to use it. It can be very different from how Postgres works. It can be named something different. It can be named something similar, but it works differently, right? So Cockroach is in the syntax to semantic level. They have different ways because they're re-implementing the Postgres engine, and it's impossible to achieve parity without reusing the code base. Now, at the highest level is runtime, which is I have something in Postgres. If I run it with you, it'll look more or less the same, right? So folks that have it, like Aurora has, runtime compatibility with Postgres, the original Aurora. And if you look at Aurora DSQL, that has more of syntax compatibility, right? So it's more a little lower form. They'll obviously improve it. It reminds me of where Yugabyte was in 2019, but there are some things architecturally that are going to be very tough for them to accommodate, like we talked about pessimistic locking and read committed.
Hmm. So, where is Yugabyte? Is there a benchmark or some place that shows what is the percentage of compatibility with Postgres?
Yeah, we have an internal benchmark we track, which is the number of Postgres unit tests, the regression tests from the Postgres suite that we can
Yeah.
run. We're right now at 91% internally when we look at it. And obviously, when we enable a feature, it's not just the fact that it works like Postgres when everything works perspective, it's also the error codes, the retry logic, the exception cases, everything works like Postgres. That's
Hmm.
something that, is implicit in the way we build it. But I think there's a very interesting, article I saw recently. It was called the Postgres Compatibility Index, PCI. Very
Oh,
recently that was published. It's a GitHub repo.
oh,
They use this to look at Yugabyte DB, Cockroach DB, and DSQL, and just to understand the Postgres compatibility of these three databases. And they put us at 88%, pretty close to our 91, so very, very close. Cockroach was in the 50s, 50%, and Aurora DSQL was in the 18%, just to give
hmm.
you a comparison.
Yeah, I was just learning about DSQL. Although, let's to be clear, DSQL just got announced 2 weeks ago. It's in preview, and it's the first version, and it'll get better over time. But I was surprised that foreign keys are not supported, triggers, UDFs. There's a lot of restriction in the product that was just announced.
Yeah,
Hmm.
yeah. I think a lot of this is also with respect to what is the market that Amazon wants to go after with this. Like,
Hmm.
are they looking at it? We're looking at it. Like, for example, we're going after business critical workloads and for enterprises. And perhaps one thing that I don't know if this is just something me reading too much into it, but if you look at serverless, for example,
Hmm.
serverless can be you could view it as auto scaling on one side, which is something we're very good at doing, or you could view it as when apps stop issuing queries, you don't want to spend money. So those are more lower end and highly variable kind of workloads
Hmm.
versus workloads that are business critical that absolutely have to survive. So it's unclear where they're orienting themselves. The words are hard to make out from their documentation, but we will know over time.
Got it.
But they are more from the looks of it targeted at greenfield applications where people can read it. So think of it as a DynamoDB with a Postgres syntax in front. Like, it's kind of like Spanner with a Postgres syntax in front. It's kind of like that rather than truly taking Postgres and making it work.
Hmm.
Because with Amazon, they have Aurora traditional for durable workloads in the cloud. They have Aurora limitless for some kinds of scalability. They have Aurora DSQL for multi-region horizontally scale. So each one has a different kind of database. And with Yugabyte, we bring it all together in one product.
Okay, very nice. One more topic I want to ask you about is open source.
Yeah.
So, do you have an open source? But even open source is now having a lot of headwinds because a lot of companies who came out with open source databases, so they're just sticking to databases, were unable to monetize it, and some have taken it back, and some are back into open source. What's going on in this space?
Yeah, so I have a very opinionated view of this market,
Okay.
obviously, because I should, because I guess we have to apply it to Yugabyte as a company. But so here's my view. I think that, like, firstly, open source works as a evaluation, adoption, distribution medium as
Hmm.
long as the tech has enough depth, enough IP,
Hmm.
and it actually controls mission critical stuff, right? So
Hmm.
when I say mission critical, I mean really mission critical, right? So if it's not, then people, like, then open source can lose out to cost, right? Like, that'll be the friction point. So companies picking it, and for us, fortunately, we're in the business of running, really mission critical apps. So that's not a problem for us, right? Now, when you take a step further, you see, for example, a company like Mongo went from open source to, not so open sourced in terms of licenses, right? It's source available, but not really open source. For them, I think the problem was they had to evangelize MongoDB. Nobody knew MongoDB before MongoDB. And so, they felt like others were probably capitalizing on their success a little too much, like the cloud providers and other people. And they went and changed their licenses in order to block that. But I think it's also important to note that they made good investments in running their own managed services through Atlas, which has been great. So they were able to give users a viable option to consume a managed service for Mongo, which worked out well. Now, when you look at other companies like, say, Elastic, Elastic is not without prior art. There was, Lucene and other search indexes before,
Hmm.
and Elastic was a long time in the open source. And the company, I guess, from what I can see from the outside, didn't embrace making it a managed service as quickly or as rapidly as, like, say, a MongoDB did. Right. So the problem was the cloud providers wanting to make their own clouds, specifically Amazon wanting to make its own cloud valuable, started putting Elastic as a service, and it became very valuable for the users to use, which naturally Elastic felt like it was getting cut out of. So they changed the license, which caused Amazon to fork it because it was such a critical piece of infrastructure, which then caused two things. And now Elastic is coming back to the open
Yeah.
source. So I think it's important to note that open source forces competition. So if you think about it a different way, had Elastic embraced the public cloud instead of gone the other way, it would have been a different story that would have played out altogether, right? So this is open source at its finest, doing its job of forcing competition across the board, right? And then there's the third one, which is like, our own competitors, Cockroach, more power to them if it works for them. But we all play, like Yugabyte, Cockroach, we play in the Postgres space, where not only is there a prior art, there's a prior database, and that's pretty
Hmm.
popular. So one of our core selling points is that, we give one of the questions people ask in transactional databases like ours, like because we play in the space of Oracle and in DB2 and SQL Server, where it's all business critical stuff, is, what happens if there's a risk I'm taking with a company like Yugabyte or Cockroach? What happens if you guys aren't around anymore? Right? Open source becomes super critical, as does Postgres as a fallback. Both of them are pretty critical. So, if you're able to tell people, look, our database is open source, you can always make sure you can service your cells. And on top of that, you can go back to Postgres. Anything you write on Yugabyte will work on Postgres. That works really well for us. So for us, being as open source as Postgres is super important for our business model. So it's not just like one part of just, marketing and getting, it's truly a part of the business model. And it's helped us a lot. It helped us, grow and get a lot of traction. For Cockroach, I don't know how they see the market or who they're going after, but yeah, I
Got
would
it.
say for us, it's becoming a buying pattern almost in some of the largest enterprises,
Right.
because after Oracle's, you know, the tough time they've had with Oracle licenses and cost, for everyone, open
Yeah.
source is an
The,
important
the,
criteria.
yeah, and there's also Redis, which also changed their licensing
Changed
model.
back, yeah, changed and
And
changed back. That's right.
within 24 hours, Valkey
Valkyrie, yeah, yeah, yeah.
came out, and now Valky is seeing success, and I can see the reverberations of what's happening because I just saw recently the creator of Redis, Salvatore, he's now back into Redis Labs. So we see a lot of movement in this space, and the story is yet to be finished, but let's keep moving on. Have so many questions. I don't want this to become like a Lex Friedman 3 hour podcast. So I'm gonna move ahead. I had questions about deployment and scalability, but if you have time, we'll come back to that. But I want to ask you a very critical question about what are some challenges and opportunities that are yet to be addressed? You said you started data company in 2016, so now it's 9 years, almost 9 years.
Yeah.
It, I've heard it takes 10 years to build a database. So what else needs to be addressed?
No, I think this is a great question. I think, I can tell you that I was fighting that it takes 10 years until it takes about 10 years. I mean, at 7 or 8 years, you're almost at 10 years.
Yes.
But no, I think what is looking ahead for us is very exciting. We are completing our Postgres compatibility matrix. So we are, getting to a spot where a lot of Postgres applications can modernize very quickly onto Yugabyte. We built an AI-based modernization,
Mm.
pilot, so to speak, or agent, whatever you want to call it. It's called Voyager. It's also open source.
Mm.
That's helping look at the source databases and help people modernize to Yugabyte DB in a private or public cloud architecture. So, that's very exciting for us. I think that's something where we're focused on a lot more in order to help, bring the move. There are still a few use cases that we need, so a few features that we need to complete. These are the esoteric features in Postgres, so that is one that we have to complete. ultimately we see ourselves as, everything in Postgres is everything in Yugabyte. But if you're going to a cloud native architecture, Yugabyte will help you get there. So we see ourselves as a part of Postgres almost, right? So from that perspective, some of the other things, AI is a huge part. We're putting huge levels of investment in. We are integrating directly with some of the open source libraries in AI. So this is a step beyond what Postgres has done while making
Hmm.
it resilient and sharded and scalable. So very excited about what that world holds for us and how we can unlock the potential on that side.
I
We
have
do
a
see different
question.
demand. Yeah.
Yeah,
Yeah, go
I have a
ahead.
question on the AI support. So PG Vector has stood out as a really good package to store vector embeddings and enable vector search. How does PG Vector change in a distributed database?
So PG Vector is the interface for using it, so which remains the same. It already works with Yugabyte DB. This was our promise behind Postgres compatibility, zero friction in adoption, right? But what changes under the hood for us is we can expose a lot more options in PG vector to get a much richer set of functionality from the vector indexes itself. Because instead of using PG's re-implementation of the vector algorithms, we are going directly to the source, which is open source databases, open source libraries like usearch and FICE and some of these other vector implementation algorithms that we are putting alongside the data itself. So that's number one. So richer data set. Second thing is, we'll be able to shard and replicate and, scale horizontally or vertically data sets alongside, like the vector indexes alongside the data set. So that's just transparent to the user. And it's as simple as using another index, just like with PG vector, but the index itself scales and does its thing right under the hood. So that's another, like, huge benefit. And the third one is, you don't need to go and put different instances of the database, even though it's PG, one to run the app, one to do the vector indexing, because these are resource hungry, right? And this is something we can quite efficiently and effectively help people scale and improve the life cycle of the application, which improves ultimately the velocity of building the app or velocity of releasing the features.
That is great. And then for indexing, do you use Meta's Face, HNSW? Uh,
All of it. So we're picking a few right now, but the way we've built it is, there's multiple implementations from multiple libraries. It'd be as much as like a little bit of DDL metadata with this equals that, and you can use any library, any algorithm. So that's the way we're democratizing
Got
this.
it. So in this space of distributed SQL databases, there are now a number of companies. How do you see the competitive landscape evolving?
So the way I see it is there is only two axes. There is
Hmm,
a Postgres feature set axis.
hmm,
And once you go beyond Postgres, you're looking at what does traditional commercial databases like Oracle, SQL Server, DB2, what do they have that Postgres doesn't? So, that's one axis, which is the functional capability of the database.
hmm.
And there's a cloud native architecture or distributed architecture axis. So things like auto scaling or serverless or like, other things like what does that look like, right? So the way we see it is that you need to be above a certain threshold on the Postgres axis in order, or the functionality axis of the database, in order to truly have the Postgres innovation lift the boat of the database. And we are there. So, the other databases that are there are like Aurora or like, Neon. We see some databases there, Alloy, etc. And, when you look at the x-axis, which is the truly cloud native shared nothing axis, we see ourselves as, being architected in a shared nothing way, like Spanner, like Dynamo, like DSQ, all the way to the extreme of cloud native architecture. So we can handle anything that comes our way compared to what an Aurora or Neon does. So we should be hybridizing the two worlds. That's really how we see it. We continue to hold the position, like our view is that both these axes will be independent, like innovation dimensions. And we see ourselves as taking the innovation dimension from Postgres and bringing it into cloud native. So that's the cycle that we enable.
Sometimes I hear this notion that distributed SQL is only for the most complex use cases, hence it's a niche category. How is Yugabyte attracting new customers in this competitive landscape you just talked about?
Yeah, that's a great question. In fact, just 2 months ago, we announced our latest feature set, which is more and more compatible with like what an Aurora would run like. So where Aurora and Aurora DSQL are two separate offerings, think if they were a single offering, that's what
Hmm,
Yuga is
I
is
see.
becoming,
Got
right?
it.
So that means when the
Right.
data set is small, it starts
Yeah.
to match how Postgres works.
Mhm.
So We call this the adaptive cost-based optimizer. That's really what gives us the edge. When the data set is small, it works like Postgres. When the data set is large and you have to do sharding, distribution,
Mm.
multi-region, it switches into running efficient plans and optimization for multi-region workloads. So it's transparent. It can happen on the fly. So users don't need to think about it. And we have a copilot called the Perf Advisor, which will tell the user where they can improve and get better
Mm.
things out of the system as they've configured it. So I think all of those are working in tandem to make sure that we're not just for a highly demanding workload, but are going mainstream, right? And again, the announcement by Aurora, more and more, companies joining the distributed SQL bandwagon kind of legitimizes that as the offering of choice for cloud
Yeah.
environments.
I also thought of something interesting, whether it's AWS or Google Cloud, for them, distribution means multiple regions, but within their own cloud, because they rely on hardware clocks and
Yep.
all of that. But with your logical clocks, you can go cross-cloud, even on
Yes.
premises, and you don't have any limits on how you can
No, yeah, and
scale.
that is a very important point. 3 years ago, this used to be a theoretical point. Now it's
Hmm.
real. Multi-cloud, hybrid,
Yeah.
on-prem, all of this is real. So yes, I think
Yeah,
very, very good.
I've seen many countries actually have this issue with cloud concentration, so they want their products to actually support multiple
Multiple
clouds.
clouds, yes, and be present in multiple clouds simultaneously. Yes, that's
Do
right.
you see that? Like, is that happening? Do you have actual real life customers that are
Yes, we have
adopting
real
it?
life customers. Again, not yet publicly shareable, but we do have
I
real
see.
life customers. Like, for example, I do know, like, as just an anecdote in India, the banking sector, they're looking at multi-cloud presence as a vendor de-risk strategy. And I'm hearing about that's just one concrete example, but it's happening in multiple different places. So it's happening all over the place.
That is great. So that itself is a reason, like for like GDPR or data privacy, kind of data residency laws. That itself is a reason why this category is going to become mainstream
That's
because
right.
you need to to uh, to have these regulations be taken care of.
That's
So
right. That's right. I think three dimensions. One is the resilience and scale needs of an
hmm,
increasingly digitizing economy,
correct.
right? And the second
Right.
one is the cost and regulation pressure of
Hmm,
having to be in multiple clouds or private cloud because
yeah,
you want leverage, right, over negotiations. And the
yeah.
third one is regulations and ability to build, fast enough to these new regulations. All three things are pushing distributed SQL mainstream. Right.
Amazing.
And of
So,
course, add the bridging the gap towards traditional that we're doing. And so
yeah.
we like it'll become more of a why not instead of why to.
Oh, wow. Very nice. What are some of the milestones you're most proud of since starting Yugabyte?
So for me, the first biggest milestone was launching the company publicly, end of
Hmm,
2017. We started in 2016 early, but business model, product, customers, so we had worked with a lot of customers. So we're just launching ourselves in the December of 2017, super proud. Mid 2018, we went live with our first few customers. So very proud of that. 2019 and 20, our community just took off. It blew up.
hmm,
So super, super proud of that. I think 2018 and 19 early is when we got our messaging right also. That was incredibly hard, man. I tell you, like that messaging piece is not to be underestimated, but that was again a milestone. And I'd say around mid 21, early 22 is when we really found like what I'd say, like all of this product market fit through read committed isolation, all of that. So it was pretty clear that the market was dictating, what they wanted, how they wanted, when they'd adopt the next. So it kind of gets written by itself. So I'd say all of these are huge milestones that we're proud of. We also bet on Kubernetes fairly early and had a
hmm,
Kubernetes deployment in mid
yeah.
2018. Again, very proud of it given. So bunch of things to be proud of. I think the upcoming milestones where we are increasingly and nearly fully Postgres compatible for like cloud deployments, just lift and shift, and with Voyager based assist, that's another huge milestone for us that's coming up. So yeah, I think a lot of good stuff to be proud of.
Yeah, very impressive. I am so happy we've covered so much ground. Thank you so much for staying longer. I have two last questions, and they're more on personal side. What advice would you give to listeners looking to build their careers in the data space? And my last question that I'd love for you to share is what's something share something about your life that the world in general does not know.
Okay. So let's do the first one first, which is the
Okay.
advice. I would say, like, if I would say be fearless to experiment. I mean, this may sound like a Yugabyte TV pitch. It's not. It's really that, everything in the cloud world is changing so fast.
Hmm.
And, we have all these traditional notions of, there's folks that'll come from an Oracle background or like some of those traditional database background that'll think all of this is just in the moon, up in the sky. It's not even real. And there's people from Postgres background that would say Postgres is enough for me, nothing else is needed. Sometimes it's not the technology, it's the way of thinking, right? That becomes super important. So experimentation, getting your hands dirty,
Hmm.
trying to truly understand, that's the only way to move forward. Otherwise, it's kind of like the unknown problem, right? You don't know something and that's holding you back. And how do you go learn it if you don't know it? So experimentation is the quickest way to
Hmm.
getting there. So, that's something that I would say with Yugabyte DB or with any other cloud native technology, like, keep working towards understanding it, even if you're not actively using it, and you will eventually figure out where the industry is headed. I think that's, it's accelerating, right, in the modern time. So it's just good to do that. So that'd be the biggest thing that I'd say, like, as a takeaway. Um, in terms of my personal life, I think, let me see, one of the things I do very passionately, I surf. I surf
Oh,
and windsurf and sail a lot. Yeah, I used to compete in, sailing regattas. So,
oh,
so,
wow.
so that's something probably a little less known about me.
Yeah.
Surf the
And
Indian
where do
Ocean.
you sail? Which do you have a favorite spot you go to?
I do have a bunch of favorite spots. So there's a place, I live in the Bay Area, San Francisco Bay Area, and there's a place, Capitola, nearby.
Hmm,
That's
sure,
a
sure.
great place for surfing. And
Okay.
there's another place called Third Avenue, which is actually pretty close. That's my favorite spot for windsurfing, kite surfing, all of the wind-based water sports. So yeah, so those are the two big ones.
Right.
I
What
used
about in
to
San Francisco City itself?
I I've gone to Chrissy Fields. That's my
Okay. Yeah.
yeah. That's near the Golden Gate Bridge. It's a little bit under the Golden Gate Bridge, so that's
Yeah.
a great place also. Great scenic views, everything. Yeah, sailing a lot less than before, just time. But yeah,
Did you ever watch that sailing thing where Oracle was
yeah,
competing and they had lost 9 of the 10 races and then they won 10 races in a row,
yeah. This is the America's Cup. Yes, absolutely.
America's Cup.
America's Cup. Those are yeah, different level of sailing. The boats are so specialized, millions of dollars into the boats. Yes, I do watch it though. It's a lot of fun. So as a sailboat regatta enthusiast myself, I love those things. Yeah, so I do watch that.
Yeah. This has been so amazing. Thank you so much. I love this conversation. I think people who are listening to it will really get a very clear understanding of how to parse this space. And I hope, for the listeners, we demystified it. Thank you so much for joining us. Until next time, thank you, Karthik. And we will be back soon with another episode. Thank you.
Thanks.